Hello student, the last class we discussed the problems related to the chemical equilibrium, and now we are discussing the relation between Kp, Kc and then the factors which can affect the equilibrium constant. Let us focus on that one. Suppose whenever any reactions will be there, suppose for our convenience I am taking a reactions small a, small b, and this gives rise to is nothing but a small c and then small d like this. And now small a, b, c, d is nothing but a what, my dear? Is nothing but a stoichiometric coefficient. So then small a, b, c, d is nothing but a what? Stoichiometric coefficient. Stoichiometric coefficient. And then if you look at over here, directly I can write down the equilibrium constant in terms of a concentration is nothing but a what? Kc. So then Kc will be equals to, I can write down directly active mass or molar concentration of the product raised to the power of the stoichiometric coefficient by active mass or molar concentration of the reactant raised to the power of the stoichiometric coefficient. Same way I am writing, you look at active mass or molar concentrations of the product raised to the power of the stoichiometric coefficient by active mass or molar concentration of the reactant raised to the power of the stoichiometric coefficient. These things you have to understand. And some people, some student has a misconception. Here they used to write down class this into this. You have to understand this. Here the sign will be what? This into this. This into this. It's not a plus sign. Clear? And now you look at this is a expression of Kc. And then the expression of Kp, equilibrium constant, in terms of a partial pressure, Kp will be equals to what? The partial pressure of the product raised to the power of the stoichiometric coefficient by partial pressure of reactant raised to the power of their stoichiometric coefficient. The same way I am writing over here the partial pressure of C raised to the power of the stoichiometric coefficient into partial pressure of D raised to the power of the stoichiometric coefficient by partial pressure of A raised to the power of the stoichiometric coefficient into partial pressure of B raised to the power of the stoichiometric coefficient. Already we write down this is Kp in terms of a, this is these things. Now you look at here itself I am writing that already we know from the ideal gas equation what we know, my dear? PV will be equals to nRT. From the ideal gas equation, from the states of matter we know PV will be equals to nRT, where P is the pressure, V is the volume of the gases, N is the number of moles of the gases, R is a universal gas constant, T is the temperature in Kelvin scale. So then from here itself we can write down P will be equals to N by V into RT. P will be equals to N by V into RT. N by V is nothing but a number of moles by volume. So that is why number of moles by volume is nothing but a molarity. And then molarity is nothing but a active mass. So then P will be equals to, we can write down the active mass into RT, because active mass is nothing but a part of a molar concentration. So then we can write down like this way. Then you look at, I can write down over here itself, if you look at, then the partial pressure of C will be equals to, I can write down the active mass of C into RT. Partial pressure of D I can write down active mass of D into RT. And then partial pressure of A we can write down active mass of A into RT. And then partial pressure of B I can write down active mass of B into RT. I can write down like this way. And now these things I am writing this expression of Kp. Already we know the Kp will be equals to partial pressure of C raised to the power of the stoichiometric coefficient is nothing but a small c. The partial pressure of C is nothing but these things. I can write down like this, RT to the power C by into partial pressure of D is nothing but these things. Partial pressure of D to the power small d, which is a stoichiometric coefficient. Then I can write down this way, these things, RT to the power small d. This is the Kp expression I am writing. And then this is a PA. PA will be equals to these things I am writing. You look at like that, I can write down and B also I can write down like this way. B also I can write down like this way. Now you look at this on arrangement, I can write down like this. This things is nothing but a this, and then RT, this will be nothing but a C plus D, overall C plus D, and here these things will be nothing but a this, and this will be nothing but a this, and this part will be nothing but a what? Kc. So then I can write down Kp, and here RT to the power A plus B, and then Kp will be equals to this part will be nothing but a Kc. I can write down Kc RT to the power C plus D minus A plus B, and this part we can write down what? This part we can write down delta Ng. Delta Ng we can write down delta Ng. Clear? And then or some book generally for the gaseous reactions, so we can write down delta N, some book used to write down. So then Kp will be equals to Kc R to the power what? Delta N. Generally delta Ng for the gaseous reactions. So Kp will be equals to Kc delta N, and then delta N will be equals to nothing but a C plus D minus A plus B. That means total number of moles of the product minus total number of moles of the reactant. Total number of moles of the gaseous product minus total number of moles of the reactant. So then the Kp-Kc relation, what it is coming? Kp will be equals to Kc R to the power delta N. And now you look at if the delta N will be equals to 0, so then sum to the power 0 means 1. So then Kp will be equals to what? Kp will be equals to Kc. If delta N is greater than 0, that means positive. So then delta N positive means Kp will be equals to Kc. If you multiply something with Kc, then only it will be equals to Kp. So then Kp will be greater than what? Kc. And now if the delta N is less than 0, delta N is less than 0 means some R to the power suppose minus 1. This will become 1 by RT. Then with the Kp if you multiply something, then only it will be equals to Kc. So then we can write down Kc will be greater than Kp. So these are the basic things you have to understand from these relations. So then from this relation what I am telling, when the delta N will be equals to 0, so then Kp will be equals to what? Kc. Suppose I am writing delta N greater than 0, that means I am putting 1. So then if you look at Kp will be equals to Kc into RT. So then with the Kc if you multiply something, then only it will be equals to the Kp. Naturally Kp is bigger than Kc. So that is what I write down, Kp into Kc. And then you look at suppose delta N is less than 0. I am taking one value minus 1. So that means Kp is equal to Kc into 1 by RT. R to the power minus 1 means 1 by RT. So then Kp into RT will be equals to Kc. So that means with Kp if you multiply something, then only it will be equals to Kc. So that is why Kc is greater than Kp. So that is what you have to understand this logic. And now this is a relation between Kp and Kc. They will give you a certain reaction and they will have to told you find out they will give you the Kp value. Suppose they will give you any reaction. Suppose they are giving you N2 plus 3H2 is nothing but a 2NH3. And then they will tell you initial number of moles they will tell you, and then they will tell you at equilibrium the number of moles what is there, and the initial pressure they will tell you. As the pressure is directly proportional to number of moles, so then the equilibrium pressure also you can find out. From there you will get the Kp value. Once you will get the Kp value, they will ask you the question. They will not give you the Kp value to you. They will give you the pressure, initial pressure or initial number of moles, and then they will tell you that at equilibrium what will be the number of moles. From that you have to find out the equilibrium pressure and each component partial pressure. From there you will get the value of Kp. Once you will get the value of Kp, then you can put the relation. Kp will be equals to Kc R to the power T delta N. They will provide the temperature. Then you can get the Kc value. This type of problem also they can construct. So that is what you have to understand very nicely. And then with this thing, suppose with the Kx, what will be the relation between this is a Kp-Kc relation. With the Kx, what will be the relation? So suppose the Kx, if you look at the Kx relations, we are doing now the relation with the Kx. If you look at Kx is nothing but a mole fractions. So then the mole fractions, if you look at that relations with the mole fractions. Here I am writing these mole fractions relations. For the same reactions, I am doing with mole fractions. We are doing with the relations with the mole fractions. The mole fractions, here the relations Kx will be equals to mole fraction of product raised to the power of the stoichiometric coefficient by mole fraction of reactant raised to the power of the stoichiometric coefficient. These things will be there like this. These things will be there like this. Okay. And now, because of these expressions, what we write down over here itself, mole fraction, and then already we know the partial pressure of a particular component. If I write down the partial pressure of a particular component will be equals to mole fraction into total pressure. This is from the Dalton's partial pressure law. So that way we will write down, instead of this expression, Kp expression, I can write down this way. That is nothing but what? I can write down mole fractions. The same way these things, Pd will be equals to mole fraction of D into total pressure. Pa will be equals to mole fraction of A into total pressure. Pb will be equals to mole fraction of B into total pressure. Then what I am doing, you look at, my dear student, instead of this I am writing the Pc will be equals to mole fraction into total pressure. That things will be equals to nothing but this. And then here instead of Pd we can write down mole fraction of D to the power D, and the total pressure will be like this. And then we can same way we can put it over here like A. These things will be nothing but A. These things will be nothing but a mole fraction of B into these things will be nothing but like this will be there. And then these expressions will be nothing but we can write down is nothing but a Kx into pressure delta N, where the delta N will be equals to what? Delta N will be equals to same way C plus D minus A plus B, total number of moles of the product minus total number of moles of the reactant. So then Kp will be equals to one expression we got with the Kc r to the power delta N, r to the power delta N, and then Kp will be equals to Kx p to the power delta N. These two relations we are getting. And moreover, you have to understand always equilibrium constant only on depend on temperature, not on anything. Equilibrium conditions or equilibrium constant only will depend on the temperatures, not anything else. And now these are the understanding you need to know over here. Now I am going to discuss the factors which can affect the equilibrium constant. And the next class I will start the degree of dissociation and then the relations of degree of dissociation in some reactions, and from their vapor density we will explain. And now you look at what is the different, we need to know what is the different factors which can affect the equilibrium constant. The different factors which can affect the equilibrium constant. Factors affecting the equilibrium constant. Factors affecting equilibrium constant. Factor affecting equilibrium constant. According to the Ch-7 principle, we know what are the parameters which are maintaining the equilibrium constant. If you disturb one of the parameters, the reaction will adjust in such a way so that the equilibrium constant can be same, as well as whatever change you are doing, that change can be nullified. That is nothing but a Ch-7 principle. So then suppose if you have the factors I am telling concentrations. Suppose A is converting to B, this is a equilibrium. If the concentrations of B, if it is increased, then what will happen? The equilibrium expression is nothing but the active mass or molar concentration of the product is nothing but a B by A. Suddenly you are changing the concentration. Then what will happen? More A will be formed so that the ratio will be same. That is what the equilibrium constant cannot be changed, because its name is a equilibrium constant. You look at the idea. The equilibrium constant expressions will be equal to what? B by A, active mass or molar concentration of the product by active mass or molar concentration of the reactant. Now suddenly if this concentration is increased, then this ratio has to be changed, but equilibrium constant cannot be changed. Immediately, if it will make the reaction in a backward direction, more A will be formed. When the more A will be formed, this ratio will be same value. So that is why the equilibrium constant will be the same value. That means if you increase the concentration of B, reaction will be backward directions. Reaction will be backward directions. So that way they will nullify this effect. That is what Lassertle's principle is telling. The parameters which are maintaining the equilibrium constant, if you change one of the thing, they will change in such a way so that they can nullify that effect. And now the second is, I am telling, is nothing but a pressure. Suppose if there is a reaction is there like this, PCl5, PCl3 and then chlorine, and then all are gas. And now in the product side number of moles is 2, reactant side total number of moles is nothing but a 1. And now delta N will be equals to nothing but a what? Delta N will be equals to 2 minus 1. Total number of moles of the product minus reactant will be equals to 1. And now you look at, if I increase the pressure, logic you understand, then what will happen, my dear? When you will increase the pressure, then the volume will decrease, because you know pressure is inversely proportional to volume from the Boyle's law states of matter. And then when the volume will decrease, then the number of moles by unit volume, that one will increase. So because the volume is decreasing, number of moles per unit volume, that one will increase. As the number of moles is increasing because of increment of pressure, then the reaction will go to that direction where that number of moles will decrease. If the reaction will go backward direction, number of moles will be 1. If the reaction will go forward direction, number of moles will be 2. But the reaction will proceed that direction, because from the increment of pressure, ultimately the number of moles will increase. That is why the reaction will be which direction? Reaction will proceed, reaction will be backward direction, Same way, if you decrease the pressure, then the volume will increase. As the volume will increase, number of moles by unit volume will be less. When the number of moles will be less, reaction will proceed towards that direction where the number of moles will increase. So that is why at forward direction, number of moles will be more. So then the reaction will be forward directions. Reaction will be forward directions. Reaction will be forward directions. This what you have to understand. So that means I explained the concentration effect on the equilibrium constant, and then pressure effect on equilibrium constant. Then if you look at the temperature effect and inert gas addition at constant volume at constant pressure. These are the things you need to know. So then in temperature, what will happen in the temperature effect? In the temperature effect, suppose there is a reaction is there. Suppose I am telling A is converting to B. This reaction, forward reaction, delta H they are telling negative. That means heat releasing. Forward reaction is heat releasing. Forward reaction, delta H negative means heat releasing. If the forward reaction is heat releasing, then from the thermodynamics we know backward will be what? Heat absorbing. By consequence, backward reaction will be heat absorbing. Backward reaction will be heat absorbing. Now, if you increase the temperature, then the forward reaction is a heat releasing. Already in forward direction if I go, heat will release more and you will increase the temperature. It is not a favorable. Then the reaction, if it is come in a back side, then what will happen? Heat will be absorbed. So that is why when temperature will increase, the reaction will backward directions. Reaction will backward directions. Backward directions. Backward direction. That is for exothermic reaction. When you will increase the temperature, the reaction will be backward direction, and it will be reverse for the endothermic reaction. If the forward reaction is endothermic, if it is temperature increase, the reaction will be what? Forward direction. That is what you have to understand. And now the addition of inert gas at constant, addition of inert gas at constant volume, at constant pressure. Addition of inert gas, addition of inert gas. Addition of inert gas at constant pressure has addition of inert gas at constant volume has no effect. At constant volume has no effect. Has no effect on equilibrium constant or the shifting of reaction. But addition of inert gas has no effect. But the addition of inert gas at constant pressure. At constant pressure you are adding the inert gas. Addition of inert gas at constant pressure. At constant pressure. Then what will happen? Pressure is constant but the volume is not a constant. So then what will happen when you are adding the inert gas at a constant pressure, then the volume will increase. As the volume will increase, the number of moles per unit volume, what? It will decrease. As the number of moles of unit volume is decreased, reaction will proceed. Reaction will be towards that direction. That direction where the number of moles will increase, towards that direction where number of moles will increase, number of moles will increase, reaction will proceed into that direction. So that is why these are the different conditions which can affect the equilibrium conditions. I hope you understand nicely. So now next class I am going to discuss degree of dissociation. Okay. Thank you very much my dear student. Thank you all.